today's video we're going to be looking at creating a servo calibration sketch for the Raspberry Pi Cryton Maker Pi board and a single servo. We are going to use the two built-in buttons on GP pins 20 and 21 to move the servo. For this program we're going to use two libraries. So we're going to import machine. This library allows us to use the GP pins, and import UTime, and this library allows us to use delays. We're going to use two variables, button 1 and button 2, and we set these as button 1 equals machine.pin on 20, and we then set it as a machine.pin as an input, and then finally machine.pin.pull down. This is so we can use the built-in resistor to hold the value of the button below 0 volts. We then need to set the servo motor pin, in this case as pin 12, so we are going to set it up as a variable called PWM1, and that equals machine.pulse-width modulation, and then in the brackets machine.pin12. The next variable we're going to set is PWM1.frequency, and this is set at 50 Hz. We have four more variables which we're going to use. Angle, which is set at 0. Minimum duty cycle is 1850. Maximum duty cycle 8300. And then we set the variable called duty cycle equals 0. As you can see, the information is here in the comments. We then go into the while true. First we have print angle. The angle will be 0 on startup. The next thing we will do is read the button to see if the buttons have been pressed. So if button 1.value has been pressed, we're going to move, in this example, the angle plus 10 degrees. If button 2.value is pressed, we'll reduce the angle by 10 degrees. We then have two if statements. These are used for limiting the angle from 0 to 180 degrees. So if the angle is greater than 180, it sets the angle to equal 180. And if the angle is less than 0, angle equals 0. The final part of the code, we start a variable called duty cycle, and that is equal to int, and then we have three brackets, maximum duty cycle minus the minimum duty cycle divided by 180 multiplied by the angle plus the minimum duty cycle. So in my case it's 8300 minus 1850, which equals 6450, divided by 180, which equals 35.833, so that's converted to 36, multiplied by the current angle plus 1850. These values will be different on yours if you alter these figures here. So if you alter your minimum duty cycle or your maximum duty cycle, your figures down here will vary slightly. So for each degree of movement, the number will increase the duty cycle by 36 for 1 degree. The next thing we have is pulse width modulation dot duty underscore 16 duty cycle. This is used to write to the GP pin a 16-bit value for the servo position, so from 1850 to 8300. The final line of code is the u.sleep. In this example I am using 0.5, so half a second. This is how long before it starts the next loop through the while true. The longer you have that set, the longer you'll have to wait holding the button for the next value to change. I would recommend sticking with 0.5 in your example. Right, I'm now going to upload this to the Raspberry Pi Pico, and as you can see in the REPL, at the moment the servo is at 0 degrees. As I press the button, you'll see the value is going up and the servo is now at 100 degrees. This you can use to set your turnouts on your model layout. You can use this once you know what the value is for the thrown or closed positions. You'll need to make a note of these so that you can set them in the next set of codes that I will demonstrate in the next few weeks. Once you are using this as a calibration, please bear in mind you need to set these to +1 and -1, which will move it very slowly. For the example, I had it at 10 because I wanted you to be able to see the servo moving quickly. Hopefully you will find these videos useful for you to be able to start using a Raspberry Pi Pico or a Kryton MakerPi board for your model layout, animations or different ideas you may have. If so, please consider liking and subscribing, as this helps us with the YouTube algorithm. Thank you again for watching.